Welcome to This Explainer. Today, we're looking at the clinical realities of multi-peak LED light curing units. This is all based on some very interesting recent data published in the Journal of Dentistry. We're going to start right off the bat with a simple clinical fact established in the literature. The marketing label multi-peak actually covers a really wide range of actual light outputs. If you assume that all these devices perform exactly the same way just because they share that category name, well, you might be introducing some unexpected variables into your restorations. Here is a quick look at the agenda we'll use to examine the data. 1. The light curing facts. 2. Why multi-peak lights. 3. Testing 8 contemporary units. 4. Spectral output variations. 5. The penetration problem. And finally, 6. Clinical takeaways for dentists. Let's jump right into section 1, the light curing facts, setting the baseline. Okay, let's look at the first law of photochemistry, also known as the Grothus-Draper law. It states that light must be absorbed by a chemical substance for a photochemical reaction to take place. This foundational law reminds us of a really vital truth. It doesn't matter how high your light curing unit's irradiance is. If the wavelength of the light being emitted doesn't match the specific photoinitiator inside your composite resin, polymerization just isn't going to happen. It's all about delivering the precise type of light, not just the brightest light. Now for section 2. Why multi-peak lights? The shift from single peak. The chemical rationale for multi-peak lights makes a lot of sense when you look at the initiators themselves. On this graph, that blue dashed line represents camphorquinone. It's the traditional initiator, and it absorbs blue light perfectly. But to help reduce yellowing, manufacturers introduced newer Narish-type LUN initiators, like Lucirin TPO and Evocirin, which you can see represented by the purple lines. Now, these require violet light to activate, and that's a wavelength that older single-peak blue lights just couldn't hit. Moving on to section 3. Testing 8 contemporary units, the methodology. So, researchers wanted to see how different units handle this dual wavelength requirement out in the real world. To do this, they tested 8 commercially available contemporary multi-peak LED units. To get really precise data, they measured the total power and spectral radiant power of these exact models using a calibrated spectral radiometer attached to an integrating sphere. Basically, this captures exactly what wavelengths are coming out of the tip and at what specific power levels. Which brings us to section 4, spectral output variations, analyzing the data. When we look closely at this spectral output data, we see some pretty stark contrasts. Take the Velo X, for example. It emits a relatively balanced blue to violet ratio of roughly 2 to 1. But then look at the other extreme. The CV215i Plus emits almost entirely blue light, delivering an area ratio exceeding 300 to 1. That is quite a surprising gap for a unit that's marketed under the exact same multi-peak umbrella, isn't it? And when you visualize these distinct emission peaks, it shows us that these units are engineered entirely differently. Some have strong, balanced peaks in both the blue and violet ranges, while others are heavily blue dominant. It really just proves that you can't take general conclusions about the efficacy of all multi-peak curing units and apply them broadly. They are all fundamentally different. Furthermore, it isn't just about the total output. The physical location of the light matters too. Tests across different positions on the light tip of units, like the pink wave, for instance, showed up to an 89% variance in blue light and a 43% variance in violet light. And that all depends on the exact millimeter you're measuring. This spatial heterogeneity means different microscopic regions of your restoration could actually be receiving vastly different amounts of energy. Let's move to section 5, the penetration problem, attenuation in composites. Now let's talk about how these specific light outputs interact with and penetrate the composite resin itself. Shorter wavelengths scatter more easily when they hit the filler particles in a composite, so violet light drops off incredibly fast. At a depth of just half a millimeter, violet light drops by 69 to 70%. By the time you reach a depth of 4 millimeters, it has essentially disappeared, dropping by 98 to 99%. And the data confirms this behavior regardless of the composite brand. Whether it's a conventional resin like Filtek Supreme or a bulk fill like Tetra Plus fill, very little violet light actually reaches the bottom of a thick restoration. Even if your multi-peak light produces adequate violet light right at the tip, it's highly unlikely to activate violet-dependent photoinitiators at the bottom of a deep proximal box. And finally, Section 6, Clinical Takeaways for Dentists. What this means for your practice. Let's distill all this research down into some practical clinical takeaways for your daily procedures. The crucial point here is that the multi-peak label does not guarantee a standard output. You just can't assume all multi-peak lights behave the same way. Also, because violet light penetrates poorly past 2 millimeters of composite, you have to understand your specific unit's emission spectrum to ensure proper curing at depth. Always match your light to your chosen composite and, of course, adhere strictly to the manufacturer's instructions for use. As we wrap up this explainer, the data leaves us with one critical evidence-based reflection for every clinician. Do you know the exact emission spectrum of the curing light sitting in your operatory right now? Understanding the precise output of your equipment is that first fundamental step to ensuring predictable, long-lasting restorations. Thanks for joining me, and keep exploring the science behind the tools you use every single day.